Questions about anything from last time? About anything? Anybody not get a paperback? Let's see, this section is particularly pretty because you we get to finally do something with all the tools we've been developing. And there's a couple of exciting theorems today. One is that a continuous function on a closed interval assumes its max and min values. So there's a point where the value of the function is actually its absolute maximum on the interval. In fact, the book likes to use that term to describe these things. So there's an absolute max and min. That's how the book expresses this fact. Okay, yeah.
Does the interval have to be closed?
Yes. I'm going to do some examples to show you why that's the case. In fact, so maybe it's a good idea to start with some examples just to think about it. Okay, here's an example. Let's see, so here's a typical example. I might have a function that does some wiggling. So let's say it starts here, wiggles around, and then goes up. Here's A, here's B. That's a continuous function on a closed interval, AB. And here, the max is the right endpoint, and the min is the left endpoint. Doesn't have to look like that, though. I could have another one that goes like this. Then the min would be the left endpoint, but the max here would be right here. And the max is attained in this picture. There's actually a point. Let's see, in the left one, there'd be the A and the B endpoints where the max is attained. But this one, the max would be attained right here. So there's actually a spot that attains that max. And here, the min would be A. And I could have made one where the min was the bottom of a hump, if I wanted to. Let's see, they don't have to be nice and... You might start thinking about Rolle's theorem and calculus. But you can have continuous functions that have kinks. Oh, how about I make one where the min is down here, and the max might be a kink. So in this one, the min is right there. The max is a kink. And there's spots where they're actually attained. And of course, easy to think of examples where there's lots of things that are the max. So for example, I could have a dotted line like that. The max could be attained multiple times. Could be a kink, could even be an endpoint. So there's not just, it might not be that there's just one max, there could be a bunch of maxes. And of course, if the thing was not a closed interval, that first example, if I didn't include the endpoints there, well then that max at B wouldn't be attained. That's outside the interval. That's clearly the supremum of all the values that max occurs. And so if B wasn't in there, it wouldn't be attained. The sup would be the same thing, but it wouldn't actually be attained by a value. So there can be okay. There could be infinitely many places where the max is attained. So let's do a case like that. Well, maybe I'll do a min this time. There's a min. I could have it start out here and then go down and just sit on the min for a while. And it could come back and do it again maybe. So it can be attained infinitely many times. Here's this on those intervals. Infinitely many spots where the min is attained. Here's the max. So all I have to show you in today's theorem is that there is at least one. Okay, and I kind of like this example to realize how wild and crazy things get. I showed you this function. That's right, h of x rather, equals 0 at x equals 0 and equals x times sine 1 over x if x is unequal to 0. That thing was squeezed between plus and minus x, and it wiggles like hell as you get near the origin, but the wiggles get smaller and smaller and get squished into 0. So that was it's continuous. Let's do it on minus 1, 1. Okay, and now let's think about let me graph h of x squared. I guess I should remind you what the graph of h looks like. It looks like I'll have a x and I'll have a minus x graph. X. This is minus x. And as sine 1 over x wiggles, it's going to be 0 at 0. As sine 1 over x wiggles, when it's plus 1, it's on the purple. When it's minus 1, it's on the orange, and it wiggles lots of times as it goes in there. And let's see, it's an even function, so it would be a reflection over here, like that. So that's the graph of h of x. Now let's think about h of x squared. That's going to make it a positive thing. So let's see, h of x squared is going to be kind of nifty to look at. Both of those, the purple thing and the orange thing, when I square them, are going to be a parabola. X squared. So this is going to look like, doggone it, purple and orange thing, it's going to be a parabola. And now h, well, let's see, h is always greater than or equal to 0. So now the bottom thing is going to be the zero axis, the x-axis. And h is going to look like this. When it's on either the purple or the orange, it's going to be up like this. And then it's going to be 0, and it piles up and it's 0 at the origin, the square of a continuous function is continuous. Looks like that. And notice that has infinitely many minimums. The min is attained infinitely many times. So I've shown you now an example. Between -1 and +1, on -1, 1, the minimum value is attained at those isolated points, infinitely many isolated points, and they pile up at the origin. Let's see, there are infinitely many isolated points that are unequal to 0, and at 0, which is a cluster point. Is a cluster point of the set where, so it can be pretty wild and crazy. That's why it's amazing that this theorem is so straightforward. And of course, if I wanted to make maxes, I would take 1 minus that, or maybe 2 minus that. 2, did I say that was h of t squared? Yeah, this blue thing is h of t squared. And 2 minus h of t squared does the same thing with maxes. If I really want to get wild and crazy, I would think of something that does both. I don't want to get that wild and crazy, though. Questions about that? The importance of having a closed interval here is, I've shown you that it can't be an open interval, so the theorem fails. No such theorem for non-closed intervals. So half open or open. Because the max and min can often occur at the endpoints. And I guess I should emphasize the max and the min is equal to the sup and inf. And can occur at the endpoints. Also, if you're thinking about maybe this is a true thing for other kinds of sets, a key example that we've seen is, let's take f of a rational number, q, equals how about 2 minus q squared? For q in the rational numbers between -1 and +1. Let's see, what does that look like? I'm trying to say here. Oh, that doesn't have a zero, right? Oops. I thought I wouldn't have to think about this. That's never. Okay, the square root of 2 is irrational. So that's never 0. Minus 2, is that what I want? Q squared minus 2. That should, you think, where's that a minimum? It would be a minimum. Yeah. That would be a minimum where where Q. Anyway, if when I take a limit to get the minimum and maximum points, it's the completeness property is important. And I'll come up with an example next time that shows if you don't have the completeness property, for example, for the rational numbers, this whole thing is going to bomb. Okay, so now I'm going to give you the proof of the theorem. It's fun. The theorem is going to use a key point. Well, it's going to use the Bolzano-Weierstrass theorem in a key way. But when we first talked about soups, okay, so what is the max is going to be? Now we know that a function is bounded on a closed interval AB. And so obviously here's where the max is going to happen. And we know it's bounded, so there's upper bounds. There's an upper bound. And as we slide that upper bound down, we're going to get a least upper bound. So we expect the least upper bound to be the place where the maximum, that's going to be the max. Okay? So you slide that dotted line down until you can't slide anymore, and that gives you the least upper bound, and we expect that the max I'll call M as the max, we're going to get it, is equal to the sup of f of x such that x is in my closed interval. Okay, there's a symbol for that set we developed back. That's f of I. Okay, at the moment, we don't know that the max is the sup. So we're going to call this S star for the sup. The book calls it S star. I'm going to call it capital S. Okay, we expect that. And there was a key property of soups that we demonstrated soon after defining it. And we were doing that because of this moment today. So recall the property if S is the sup of that set, and epsilon is bigger than 0, then there must be a point in the set y in the set such that f of y, I mean, not f of y is in the set, y is equal to, y is greater than the sup minus epsilon. Okay, and we made a big deal out of that, and this was kind of equivalent to the property of being a sup, that you can do this for every epsilon. This is the easy direction, because if there wasn't such a y, then we have a smaller upper bound. If not, s minus epsilon would be a smaller upper bound. And of course, the sup is the least upper bound. That's a contradiction. So that's no biggie. And so now, when I do this, here's the construction. I'm going to let the epsilon be equal to 1 over n for n a natural number. And let's say my y is in f of I. So I'm going to write y is in f of I. So it's equal to f of x for some x. Let's call it y sub n. So y sub n is equal to f of x sub n for some x. X sub n in the closed interval. Okay. And so now I have the sup minus 1 over n is less than f of xn, and that's less than or equal to the sup. And that should make you think of the squeeze theorem, except I don't have a limit at the moment. Well, let's see, I do have a f of xn. Those are definitely squeezed in there. But the xn's don't have to converge to anything. That's what's bugging me at the moment. The xn's could be going all over the place, especially like in that picture where I had like infinitely many isolated spots where the max or min is attained. That would be a weird thing. But this is the key moment. What's this magic word here? Yeah. No, it's Bolzano-Weierstrass. The xn's are in the closed interval I. So xn is a bounded sequence. And Bolzano-Weierstrass says that a bounded sequence has a convergent subsequence. So there is a convergent subsequence, x and k, and it would converge to something, c. And because AB is a closed interval, that C is in that closed interval. I is closed, so C is in I. I guess let's see, why is that? We have A is less than or equal to XN is less than or equal to B. And so when you do the limit, the squeeze theorem, you'd have that A is less than or equal to the limit here. is less than or equal to b. Okay, and now we can do the squeeze theorem. I would have S minus 1 over nk is less than f of x nk less than or equal to S. F is continuous. So this is I'm using the fact that f is continuous. And so this goes to f of c, and of course these go to, this one goes to s, and in the limit they'd be less than or equal to. And so I found a spot where the soup is attained. So f of c is equal to the soup, and that's where the max is attained. So we may call S equal f of c the absolute max. Now we'll call it M. And very analogous argument using inf in place of soup. You know, I'd start with a lower bound and I'd push it up until it just barely touches the graph. That would be where the min, or a bunch of mins, occurs. But I won't do it. It's very similar reasoning for the min. I always call the min little m, and that would be the inf of f of I. Questions about that? For the Bolzano-Weierstrass, this is where the Bolzano-Weierstrass theorem is critical. Well, now there's some kind of fun things to do to introduce the idea. I'll talk about the bisection method for finding zeros. The book doesn't draw any pictures, so I think it's more fun if you draw pictures. If I can do it. I want a function. Make it look like that. Here's an A. Here's B. In my example here, I'm going to assume that f of A is less than 0 and f of B is bigger than 0. I'm going to find you a spot between there, C. So the deal is there is a C with A less than C less than B with f of C equals 0. There might be multiple ones. If that thing wiggled a lot, there could be multiple C's. In fact, there could be infinitely many C's if I made it totally flat for a while. Okay, and the bisection method, here's the idea. I first bisect. I'll take the midpoint here. Let's call this an A1 and a B1, because I'm going to do this again and again. This is the midpoint. A1 plus B1 over 2. Well, in my picture here, the value of the function at the midpoint is positive. So here on the right-hand side of that interval, I'd have two things that are positive. So as in the picture, there is no zero between the two other endpoints. There could be if I made it wiggle a lot. But the left-hand side, now I have the left side is 0 and the right side is positive. So now I know there's a 0 in the left-hand side of that. Okay, and I'm just going to keep doing that. So this is the midpoint. I'll call it M. What am I going to do? Midpoint M, that would be A1 plus B1 over 2. That's the midpoint. And if f of the midpoint is positive, then I'm going to have a new interval. A2 is going to be A1, and B2 is going to be equal to the midpoint. That's a new interval. And if it's negative, then I'd have a positive thing on the right and a negative one on the left. My new interval would be A2 would be the midpoint, and B2 would be B1, the next interval. I guess remember the trichotomy thing. If it's equal to 0, we're done. I found a 0. Quit. We found a 0. Think of this as a computer problem. So I'm computing these values and just following my nose by an algorithm. Question? This thing might not be a differentiable function. There are continuous functions that are nowhere differentiable. So this works no matter what. Yes, if you're thinking of Newton's method or, some fancy calculus, we don't have that at our disposal here. We just have a continuous function. And they can be incredibly weird and, in fact, non-differentiable. I'm only looking for one. They could be zeros all over the place. I just want to demonstrate that there's at least one and I can find it. Okay, and so now we keep repeating this. Well, let's say note B2 minus A2, the length of the interval, would be B1 minus A1 over 2. And as I repeat this, I keep dividing by 2. Okay, repeat. And I get a nested sequence of intervals. So let's see in my picture above. Next time I repeat it, the next midpoint would be right here. Then the two left ones would be, so I guess I can call the green one the first time I do it, and the orange one the second time I do it. And then my next interval would be actually the one between the two midpoints. And my next midpoint would be slightly to the right of the 0 I'm looking for. That's not really visible, is it? Etc. So I get a nested sequence of closed intervals. And the length of the, so let's see, I'd get A1, B1 would contain my A2, B2, would contain, etc. And the length of those Bn minus An would be 1 over 2 to the n. Let's see, n minus 1 actually, times B1 minus A1. Goes to 0 as n goes to infinity. And so the nested closed interval theorem, we know that the intersection of those intervals, let's call this, use I sub n's, is a single point. And it would be a single point in my original interval. Well, of course, that's got to be where it's 0. Think about it. So I next claim f of p is a 0. And let's think about why that's true. We would have that f of an, what do I have? Yeah, the left ones are always negative, and the right ones are always positive. So the fn f of an is less than 0. F of bn is greater than 0. And the an's and the bn's are both tending to p. And so if all the things are less than 0 and they tend to something, the limit has to be less than or equal to 0. And these are tending also to f of p. And so their f of p would also have to be greater than or equal to 0. Well, the only way both of those things are true is if f of p is equal to 0. I guess note, I kind of used the squeeze theorem here. Let's see, what did I know? I know that an is less than or equal to p is less than or equal to bn. And the an's, the distance between the an's and the bn's are tending to 0. Implies an goes to p, goes to p. Anyway, that's how you do it. And actually, if I was going to write you a computer program to go through those steps, it would zero in pretty quick. Let's see, because 1 over 2 to the n gets small really fast. So I'd find my 0 in an interval of size 1 over 2 to the n really pretty quick. And when 1 over 2 to the n is less than machine 0, engineers and numerical analysts call it quits. They found it within the accuracy of their computers. And great day now, I can use something like Maple, where I can make the number of digits 50 if I want. So I could find the 0 to 50 decimal places in no time. I shouldn't say the 0, I should say a 0. Of course, there was nothing fancy about 0, nothing special about 0. I could repeat this argument with, I can apply this routine I can apply this routine to f of x minus something. Prove the intermediate value theorem that you learned in freshman calculus. If f is continuous on a closed interval, got to be a closed interval. AB and f of A is less than L is less than f of B, or f of A is greater than L is greater than f of B. Then there's a spot between A and B where L is hit. So there's a C with A less than C less than B, where f of C equals L, the intermediate value. Exactly the same. I would just take my function minus L and do the bisection method. Bisection method. Or let's see, if I wanted to have the left side negative and the right side positive, I'd take f of x minus L. And if I wanted to do the other case, I would take L minus f of x. So the picture, of course, is, let's see, let's think of some pictures. There's an A, here's a B. Here's a spot where the intermediate value is attained 1, 2, 3 times. So there's 3 C's that work. C1, C2, C3. And if I did one up here, there'd only be one. But I can't find one where there isn't any one. Okay, and in this case, f of A is the small one, and f of B is the big one. And now it's a natural thing to do to take the max and the min points, and then you realize everything between the max and the min gets hit. So here's an idea. Start with f on I. Get the min. and the max. And then it's a continuous function on a closed interval. We know we get an A, let's call it A2, or let's say, get a P1 with an I, where the min is attained. And a P2 where the max is attained. I have a little m for the min, where f of P2 equals m, and then do the intermediate value on the interval P1 to P2. I don't know if P1 is, we'd have to do cases. If the max is equal to the min, the thing is constant, so that's a dumb case. Case P1 equals P2, f is constant. Kind of a dumb case. Case P1 less than P2, that'd be good. But then we could do the intermediate value theorem. For the interval P1, P2. If P1 is greater than P2, then we do the intermediate value theorem for P2, P1. Anyway, what you see is that everything between the min and the max gets hit. Everything m less than or equal to L less than or equal to m gets hit. And so a fascinating thing here is that we see that the image of the interval is equal to a closed interval. So continuous functions map closed intervals to closed intervals. That's a closed interval theorem. Think about what happens if those intervals are or not closed. Well, then it turns out you can map a semi-closed interval to a closed interval, or an open interval to a closed interval, but the thing on the other side is always an interval. So think about this. F of AB, F of semi-closed, F of semi-closed this way. Turns out that the image will always be an interval of some kind, but not necessarily closed, and not necessarily the same kind. So the answer is image is an interval. But you can't say what kind.